Okay, good morning all. So yesterday we are solving problems on frames without any sway. The last three problems we have solved by slope deflection method, and that is totally for the frames without sway. Okay, so we have dealt with such problems. Now today what we'll do is we'll take up a frame wherein sway is there. Okay, so I made it in the first beginning of my class that what are sway frames and non-sway frames. Okay, just to go back for that. So here these are the conditions under which a frame will undergo sway. That is, it will be having lateral displacements of the joints. Okay, horizontal displacement of the joint. So what are the conditions that cause sway? One is the sway force or the lateral forces acting on the frame, like this one. Okay, and unsymmetry in terms of support conditions. So here we have a frame with unsymmetric support condition. One of the support is fixed, other support is hinged. So this will cause sway in the frame because of this unsymmetry in support conditions. Another condition what we have was unequal column heights. So column heights are unequal. The two columns or whatever the columns are present in the frame we are dealing with, they are of unequal heights. So this is also a case of unsymmetry. So there is a possibility that frame will sway under such condition also. Okay. Then next condition, what was there is unsymmetric properties of the column and eccentric loading, the other two conditions. What are those unsymmetric properties? The geometric properties, cross-sectional properties, that is moment of inertia of the two columns which are present in the frame. I'm saying two columns, there may be more than two columns also, but what we see is the columns what are there, they are having uh, unequal moment of inertias. Geometric properties, moment of inertias are not same for all the columns. So under such a situation, the stiffness of the column will not be same for all the columns. So that will also cause the sway of the column. Here in this frame, you can see I1, I2 are there for the two columns, and I1 and I2 are not equal. Okay, so this is one more condition. Another condition is a loading somewhere other than the middle of the span, like such eccentric loading may be present, or there may be unsymmetric loading. There may be UDL spread for this entire span, and somewhere here a vertical concentrated load is acting other than the center. A vertical concentrated load is present over there. Okay, so that violates the symmetry rule. Okay, so under this also the frame will sway in this form. Okay, this is what you see the sway is in the red line. What is shown here in a red discontinuous line, that is the sway of the frame. It has been displaced in lateral direction by an amount delta at the two top joints. Delta, this itself is sway. So now we'll start dealing with such sway frames. We'll analyze them by slope deflection method. Okay, right. So this is one example what has been taken here. Okay, and we have to analyze this frame by slope deflection method. Okay, so by observation itself, you can see this is a clear case of sway frame. Why? There are several conditions which will cause sway. Okay, first I'll be looking into whether is there any force which is causing the sway. Okay, is there any direct force which is trying to displace the frame in lateral direction? In our case, yes, it is there. Okay, this 80 kilonewton force which is applied on this AB member in horizontal direction, it will definitely make the frame to move in lateral direction. Okay, towards right, it will push the frame towards right. That is a sway. Okay, so sway will occur. One is because of this lateral force. The other condition what exists in this frame which will cause the sway is unequal height of the columns. So this member AB is of 3 meter, whereas member CD, which is also a column, is of 2 meter. Unequal column height. So that is also condition which is sufficient for the frame to sway. And also we can observe the cross-sectional properties are also not same for the two columns, 2i, 1.5i. So three conditions we can identify here, due to which the frame will undergo sway. Okay, so it is a case of sway analysis, right? Now, how to deal with such frames? How do we do the analysis of such sway frames? That we'll see in this example. Okay, so we are asked to analyze the frame by slope deflection method and draw the Benjamin diagram and the deflected shape, right? So I tried calculating the degree of static indeterminacy in this case. ds, what I have is two supports here which are fixed, three reactions over here, three reactions here, six reactions, unknown reactions totally, minus three conditions of equilibrium. That will tell you degree of static indeterminacy. It is coming out to be 3. Now what about the kinematic indeterminacy? It is also 3. So two joints and one rotation at each joint. Okay, at B rotation can take place, at C rotation can take place. So two unknown displacements exist in the form of rotation at B and C. 2 plus what we have seen is this frame can undergo sway, lateral displacement. So that itself will also be an unknown for us now in the analysis. So that has been taken here. So there are totally 3 unknown displacement that exist in this frame: theta B, theta C, and delta. Okay, we have to find out what are the values of these 3 unknowns by using slope deflection method. After that, we can go for calculating bending moments at the joints and also drawing the bending moment diagram. Okay. Now, analysis of sway frames is similar to our non-sway frames. Okay. The procedure what we follow for slope deflection equation will be same. Okay. There will be a additional step what we'll come across. We'll see that over here. But first, what I'll do is I'll calculate the fixed end moments for all these three members. What are the fixed end moments? So if I take member AB, 80 kilonewton, it is a concentrated load applied at the middle of the span. Okay, 1.5, 1.5. So it is exactly at the center of this span, 3 meters. So minus WL by 8. On this end, A, the movement will be in anti-clockwise direction. So I have taken minus, and the magnitude will be WL by 8 for a concentrated load applied at the center. This is the formula for finding the fixed end moment. So minus 80 into 3 by 8, it is coming out to be 30 kilonewton meter. MFAB. MFBA will be plus WL by 8, and that comes out as plus 30 kilonewton meter. Okay, on substituting these values of W and L. And coming to member BC, in BC what we have, there is a UDL present on the entire span of this member BC, which is of 4 meters. Intensity of UDL is 90 kilonewton per meter. Okay, so in such case what we have, the fixed end moment is given by WL square by 12. Okay, value of fixed end moment is obtained from this equation, WL square by 12. What about the directions? At joint B it will be anti-clockwise, at joint C it will be in clockwise direction. So on the basis of these directions we'll assign the signs. For anti-clockwise minus, for clockwise plus. So BC MF BC will be minus WL square by 12, that is minus 90 into 4 square divided by 12. So this comes out to be minus 30 kilonewton meter MFBC. And MFCB, so it will be in clockwise direction, and we have plus WL square by 12 here. Okay, so W 90 into span 4 meter 4 square divided by 12. So that comes out to be 30 kilonewton meter. So these four are the fixed end moments what we have values. For member CD, if I want to calculate fixed end moment, there is no load present on this member CD. So it results in 0 fixed end moment. MFCD, MFDC will be equal to 0. Okay. So with these fixed end moments, now what we'll do is we'll first write our slope deflection equations. Okay. So I'll refer this particular equation. Okay. This is the for slope deflection equation what we have. Mij, which is equal to Mfij plus 2ei by L into 2 times theta a plus theta j minus 3 delta upon L. Okay, I take the member AB first. Okay, this member AB, I'll consider that first for writing the slope deflection equation. So here what I have is MAB, that comes out to be MFAB plus 2ei by L into 2 times theta a plus theta b minus 3 delta upon L. Okay, now I have to identify whether these displacement do exist or they are 0. Okay, so at support A we have the fixed end. So what it indicates is theta A is 0. Okay, theta A is 0 because this is a fixed support. It will not allow any rotation. Okay, and other than that, at B we have rotation theta B. There will be rotation taking place at joint B. Okay, and B is allowed to move in lateral direction. There is a displacement that is occurring at joint B and C due to sway. So this is one more unknown that will exist in our frame. So theta B, theta C, and delta. We have identified kinematic indeterminacy. There we have mentioned these three. So delta will exist here. Okay. So this is the equation. Now I'll be substituting for these terms. So minus 30 MFAB plus 2E into 2I. For AB, it is 2I divided by 3 span of AB into 2 times theta A, which is 0, plus theta B minus 3 delta by L, 3 delta by 3. Okay. Now what you have to do is you have to choose a sign for delta here. Okay. You have to look what is the moment that is going to develop due to this sway. Okay, just see in this picture, you find the sway has been shown here. Okay, I shown the sway delta that is taking place in this frame. Now, because of this sway, what is happening to member AB at joint A? About joint A, this member is being rotated in clockwise direction. Okay, so whenever that member is being rotated in the clockwise direction, there will be an anti-clockwise movement that will be developed over here at this joint A. So under such a condition, okay, please keep in mind, when this member is being rotated in a clockwise direction about any joint, delta is taken positive here. Okay, so member AB is being rotated in clockwise direction about joint A, so delta sign will remain positive. Okay, so I have taken positive delta for that, plus delta. Okay, that is this minus 3 into delta over 3. I have adopted a positive delta value over here. Why? Because the member AB was being rotated in clockwise direction about joint A. I am at joint A. Okay. So on simplification of this equation, what you have is MEB will be equal to minus 30 plus 4EI by 3 into theta B minus 4EI by 3 into delta. Okay. You can check this, verify that. Once you cancel all the terms and all, you'll get this simplified equation for MEB. Okay, we'll call this as first slope deflection equation, equation number 1. Okay, I'll come to what joint B now. I'll take the member AB itself. Okay, but I'll write the slope deflection equation for member AB with respect to joint B. Okay, so it will be MBA, which is equal to MFBA plus 2EI by L. Okay, that is 2EI by 3 into theta A plus 2 times theta B minus 3 delta by L. Okay, so what is there? Theta A is 0. Okay, you can substitute for that 0. Identify what is the sign for delta. Theta B is existing, so I left it as it is, unknown theta B. Sign for delta. Now, what is the direction in which member AB is rotated about joint B? We are writing slope deflection equation with respect to joint B now. We are at joint B. So about this joint B, what is the direction of rotation of this member? I have to just draw a vertical line because original position of this member was vertical. I've drawn a line parallel to that original position. With respect to that, I have measured this direction. Okay, earlier also the same. With respect to the original position of this member AB, this direction was measured. Okay, originally this member BA was vertical. Now, due to sway, it has been rotated. There is a rotation that is taking place. First, I will draw this deformed shape. Okay, so due to that 80 kilonewton force which is applied over here, so it is trying to push the frame towards right. Okay, so I assumed that frame will sway towards right. So from B to this point, this is the sway towards right. Okay, so I have drawn that deformed shape, and with respect to the original position of the members, I've tried measuring the rotation over here. So at joint B, with respect to original vertical position of this member BA, what is the direction of rotation? It is clockwise. Okay, it is clockwise here. This will tell you. If you draw this deformed shape of the member, you'll come to know what is the original position of the rotation, the direction of rotation, what is being there. Okay, so it is important that you identify the correct direction of rotation and then assign the proper sign for this delta. Okay, if this rotation is in clockwise direction in such a way, delta is taken positive, else it will be negative. Okay, so for this member BA, MBA is equal to MFBA plus 2EI by L into theta A plus 2 times theta B minus 3 delta by L. Theta A comes out to be 0 and delta will be taken as positive, and that what it gives us, MBA is equal to 30 plus 8EI by 3 into theta B minus 4EI by 3 into delta. Okay, I have maintained the positive sign for this delta. Okay, please, if you have any doubt in that choosing the sign for delta, please you can ask that one. Make that point clear here. We are dealing with sway frames. How do we choose the sign for that delta? what you have to do is you have to assume in which direction the frame will sway. Okay, so one is here in this problem, it is very simple. There is a force which is trying to push this frame towards right. So from that, I have drawn this deflected shape. Okay, so it is trying to push that frame towards right. So it is moving towards right. I've plotted that deflected shape of the frame in this discontinuous line. Okay, this is the deflected shape of the frame. This was the original shape of the frame. Okay, this continuous line is showing us the original shape of the frame. So now I am trying to measure the rotation of the members, okay, in this frame which has undergone sway. So I have taken member AB. At joint A, it was rotated in clockwise direction. With respect to joint A, the member has been rotated in clockwise direction here. With respect to joint B, member is again rotating in the clockwise direction. So due to that clockwise direction, delta will be assigned positive sign. Okay. So like that, I have chosen the sign for this delta. For this term, minus 3 delta upon L. For that, I have chosen the sign for delta. Okay. Is that clear? How to take sign for that sway delta, whether it is positive or negative, how you are going to decide that. Anybody with a doubt in that part?
Excuse me, sir.
Yes.
Sir, in MFBC and MFCB, it is minus 120.
MFBC, MFCB.
Yes, sir.
BC.
Minus 90 into 4 square divided by 12. It is coming as minus 120.
4 square divided by 12, it comes out to be minus 120. Okay, right. So this is not correct, minus 30. Right. Okay, I'll change that one. For this instant, you just take that correction. Okay.
Okay, sir.
You can do that correction. It is 120. Fine. Anyway, let us say that the load magnitude is such that you will get a value of minus 30 and plus 30. I don't want to correct that with 120. Every other calculation will change. For that purpose, what you do is you consider this to be minus 30 plus 30 itself. Okay. Is that fine?
Yes, sir.
Okay. You just assume them MFBC and MFCB are minus 30 and plus 30. Okay. This you say that this is not 90. Okay. This is something else such that the fixed end moments in member BC are coming out to be minus 30 plus 30 with the same span. Load intensity is changing. Okay, that you take it. I want to know, other than that, in sway, are there any confusion in that part? Okay, similarly, what I'll do is when I take this member BC, when I want to write the slope deflection equation for member BC, what I have here, MBC, which is equal to MFBC plus 2EI by L into 2 times theta B plus theta C minus 3 delta upon L. Okay, so here what you have, minus 30 plus 2EI by 4, and note that theta B and theta C rotations are existing at both ends. So 2 times theta B plus theta C. What about delta? Delta, there is no relative displacement between B and C. Okay, I don't find any relative displacement of joint B and C. Okay, so they are in the same position as earlier. Okay, so you will find that they are at the same levels. Okay, there's no settlement. Only if any settlement is there, then this relative displacement will take place between the two joints in the horizontal member. Okay, or else this delta is zero now. Okay, it is same as what you do for the beams. So delta will be zero in this case in member BC. So for that, this delta is taken zero. And this is what the slope deflection equation is for member BC. So it will be minus 30 plus EI into theta B plus EI by 2 into theta C. Okay. So this is my slope deflection equation for member BC at joint B. This is the third equation what I have. Now similarly, if I take joint C, it will be MFCB plus 2EI by L into theta B plus 2 theta C minus 3 delta upon L. Okay, so on substituting these values, what you have, MFCB is 30 plus 2EI by 4, 4 meter is the span, 4 is the span of this member BC, into theta B plus 2 theta C minus delta is 0. Okay, horizontal members, delta will exist only if there is any settlement of the support or sinking of the support. Okay, sway will not affect your horizontal members. It will not affect the delta in your horizontal members. It will be coming in picture only for vertical members. Sway will affect the vertical members. Delta will be taken when you are writing slope deflection equation for the vertical members. That's way. Okay, other than that, in horizontal members like this member BC, you don't have to consider this effect of sway. So joint B and C, they are not getting displaced relatively, they are at the same level, so that's why delta is remaining 0 here. Okay, MBC and MCB. So MCB final form is 30 plus EI by 2 into theta B plus EI into theta C. This is the final form of this MCB. That is our fourth slope deflection equation. So up to now we have 4 slope deflection equation here. Okay, don't worry about this calculation mistake, sorry for that, but procedure what is to be followed, just concentrate on that. Okay, there may be slight change in the free bending diagram, that you don't worry about that. Okay, I'll give the corrected load intensity value here, this value will change. Okay, now what we have after this, there is a next member. What is that member here? In our case, the one more column CD. Okay, so MCD. Now I'll write the slope deflection equation for MCD. So it will be MFCD plus 2EI by L into 2 times theta C plus theta D minus 3 delta upon L. Okay, this will be same, no change in the slope deflection equation. Only thing is you need to identify whether displacements are there or they are 0. Okay, so theta C, joint C is allowed to rotate. Theta C will exist. Theta D, what we have in that case, if you look into this, D is with the fixed support here. Okay, so theta D cannot be there. It is 0. So what I have, theta D will be 0. Okay, that was noted earlier also. Theta D is 0. And delta will exist. Delta will exist. Okay, MFCD calculated value is 0. On member CD, no load is there. 2E into 1.5 I by 2. Okay, 1.5 I moment of inertia and 2 meters the span, and 2 times theta C, okay, unknown theta C plus theta D is 0 minus 3 delta upon 2. Okay, so delta will exist because it is a vertical member here. Okay, so if you take member CD, delta is there. There is a relative displacement between C and D. After it has swayed, C, D is here itself on this support, whereas C has been displaced in the horizontal direction. So now there's a relative displacement. Now, what are the direction of rotation? You look for that. About C, the member CD is rotated in what direction? It is in the clockwise direction. I'm measuring with respect to original position of the member C. This original position was vertical. I just drawn a vertical line from this C, okay, parallel to this one. Then I have measured the, with respect to this line, I have measured the rotation. It is clockwise. Similarly, even if you do that with respect to joint D, with respect to this original position of the member, the rotation is clockwise. So delta is positive in this member CD. At both the joints, it is taken as positive if at all the member is being rotated clockwise. Okay, this is true for these vertical members. This is how you assign the sign. Okay, so coming to that equation for member CD, so delta is taken positive minus 3 delta upon 2. Okay, so you simplify this, what you get here, 3 EI theta C minus 9 by 4 EI into delta. Fifth equation of slope deflection for member CD. Similarly, in member CD, if I come to joint D and write the slope deflection equation, what I have, MFDC plus 2EI by L into theta C plus 2 times theta D minus 3 delta upon L. Okay, theta D is 0, theta C will exist. Delta, what is the sign, is positive because it is rotating in a clockwise direction with respect to joint D. Okay, so delta will be taken positive. And this is the simplified equation for MDC. MDC, MFDC is 0, and then 3ei by 2 into theta c minus 9 by 4 ei delta. Okay, so we have 6 slope deflection equation. There were three members. So at each joint, we have written the slope deflection equation, and we are having 6 equations of slope deflection. In these 6 equations, there are 3 unknowns: theta b, theta d, theta c, and delta. Okay, now we have to find out those 3 unknowns. Please let me know if you have any doubt. Okay. Now, how do we solve those 3 unknowns? One is conditions of equilibrium. Okay, I'll take help of conditions of equilibrium. So I have condition of equilibrium applied at joint B and joint C. So what we have is summation MB, summation of moment at joint B should be 0, and summation of moment at joint C should be 0. So that has been applied. So MBA plus MBC. What are the members connected at joint B? It is BA and BC. Okay, 2 members were connected at this joint B. See, BA, BC. At C, they are CB and CD. So while writing that condition of equilibrium, we'll be considering moment in those 2 members. So at B, MBA plus MBC should be 0. Okay, so I'll use these values or the equations of MBA and MBC, which we have written in the slope deflection equation. Okay, so I have taken that equations and substituted here in this condition of equilibrium. Okay, what I will get if I simplify that condition of equilibrium is 11 ei by 3 theta b plus ei by 2 theta c minus 4 ei by 3 delta. Okay, the first condition of equilibrium, summation of moment about joint B, is giving me this particular equation. Okay, you can try simplifying this. Okay, you will get this particular equation from that. Equation number 7. Okay, from one of the condition of equilibrium. The next condition of equilibrium is summation of moment about joint C should be 0. So MCB and MCD, these are the 2 members which are connected at joint C, CB and CD. So MCB and MCD should be 0. And when I use the equations from slope deflection equation for CB and CD, and on simplifying that, this is what you have from the second condition of equilibrium: 30 plus ei by 2 into theta b plus 4 ei into theta c minus 9 by 4 ei delta is equal to 0. That is one more equation what you have. Now normally what was happening with the condition of equilibrium, we used to get the unknowns. We were able to solve for the unknowns. Now in this condition, in the condition of sway, what we have is 3 unknowns are there, whereas the equation what we are ending up with are 2. So 2 equations, 3 unknowns. It is not possible to solve here at this point of time. So we'll take help of some more conditions. What are these conditions called? They are called the Shear conditions. Okay, so we are not sufficient with condition of equilibrium. Okay, we need additional conditions to solve this sway problem. They are the Shear conditions. What is this Shear condition? It is nothing but summation Fx equal to 0. Summation of horizontal forces should be 0, and that is applied to the 2 columns here. Okay, so I've taken the 2 columns AB and CD. Okay, this is the one step what you will come across in this sway analysis. In writing the slope deflection equation, delta for sway has to be assigned a sign, and that has to be considered as an unknown. That is the difference in slope deflection equation. And when you are solving those slope deflection equation, in addition to condition of equilibrium, okay, you also have to take help of condition of shear conditions, and these shear conditions are applied for the columns. It is nothing but summation Fx equal to 0. So 2 columns are here. Okay, I have assigned the moments at the ends. I have taken the applied load 80 kilonewton at the base. Since there was a support, there will be a reaction HA over here. So this reaction, horizontal reaction, will develop. Okay, I'm not interested in vertical reaction at this point, so I have not shown it here. And what are there at the 2 joints? We have 2 movements being developed, MAB and MBA. We are trying to identify these movements. Okay, so MAB and MBA will be there at the 2 ends, A and B. Both the movements, I have considered them to be acting in clockwise direction. Still, we are not sure about their direction. I assume that both of them will turn out to be clockwise. Okay, so on that I have shown these forces. This is the free body diagram for member AB. Okay, what I have shown here is member AB, applied load 80 kilonewton, and reaction at joint A. One is the horizontal reaction HA, the other is the movement that is developed at joint A, MAB, and at B you come across the movement which is being developed, MBA. Okay, so these are the movements what will act on this member AB. Okay, this is a free body diagram. I've shown the forces. Okay, and in addition, what I have, one more column is there, CD. There also I have done the same thing. On CD, there was no load applied over here. So no force which is being applied on this member, but D was fixed. There you come across this horizontal reaction, HD, and also you'll have member movements at joint C and joint D. So here MCD, it is taken to be in clockwise direction. MDC also is taken in clockwise direction. Okay, I'm not worried about this direction. I've just taken all the movements in clockwise direction at this point. Okay, later we'll come to know on the basis of sign what are the directions. Okay, so what you have to do is to apply the shear conditions. First, you have to draw the free body diagram of the two columns in this frame. Okay, AB and CD, and show all the forces and reactions which are acting on that member. Okay, now you apply the condition of shear. Okay, so what it says, HA plus HD should be 0. Okay, sorry, HA plus HD should be equal to 80. Okay, sorry for that. There is a correction. This HA plus HD should come out to equal to this 80 kilonewton force. Okay, so this should be 80. Please, there is one more correction that I have to do. I'll take it this one with that correction later. Okay, as of now, let me proceed here. So this is what the condition is. HA plus HD should be equal to 80. Okay, this should be equal to 80. Right now, what is HA? How to get this HA? Okay, I'll tell you the corrected values later. I'll give it when I give this PPT, and I'll explain that in one more class further. But now let me proceed here. HA plus HD should come out to 80. That is, HA HD should be equal to this horizontal force 80 kilonewton. Whatever the horizontal forces are applied on the frame, you need to consider them. Okay, so from that I have to apply this shear condition. Now, what is HA equal to? I have to find what is HA and HD here. For that, what I'll do is I'll take moment about joint B. Okay, in this member AB, I'll take moment about summation of moment about joint B equal to 0. I'm applying summation of moment about joint B equal to 0. Okay, so what are the moments that are coming about joint B here in member AB? It will be HA into 3 meters. There will be movement due to this reaction HA. So HA into 3 meters, that is taken, it is in clockwise direction, plus HA into 3, plus MAB, which is also in clockwise direction, plus MBA, that is also considered in clockwise direction, minus 80 into 1.5. So this 80 kilonewton is causing an anti-clockwise movement about joint B. Okay, so I've taken summation of moments about joint B equal to 0, and I've written this equation. From this, I'll come to know what is my HA. Okay, so that HA, if I substitute for MAB and MBA, what I'll get is I'll get an equation for HA in terms of theta B and delta. Okay, I've substituted what is MAB and MBA from slope deflection equation. Okay, and I've simplified this term. I've taken all other terms except HA, all other terms towards right, to the right hand side. Okay, so what I'll get is minus 1 by 3 into this entire term is MAB. Okay, minus 30 plus 4EI by 3 into theta B minus 4EI by 3 into delta. Okay, and this term, this entire term is what? This is MBA. 30 plus 8EI by 3 into theta B minus 4EI by 3 into delta. And here it is this 80 into 1.5 minus 120. Okay, so this is minus 1 by 3. Entirely this term has been taken on the right hand side except HA. So when you simplify that, it will tell you what is HA equal to in terms of theta B and delta. So what I'm getting here, HA as 40 minus 11 by 9 EI into theta B minus 8 by 9 EI into delta. Okay, I'll call this as another equation, equation number 9. Okay, so that is 1, right? So shear condition, what it will do is you have to take the reactions acting in horizontal direction, add them and equate them to the applied force in the horizontal direction. HA plus HD should come out equal to 80 kilonewton here. Okay, and how to get HA? Take this column AB, wherever in which member the HA is there. I'll take about the moments, summation of moment about this joint B. Okay, summation of moment due to all the forces about joint B and equate it to 0. So from that I can get what is HA equal to like this in the form of equation, in the form of unknowns. Okay, so that is one HA reaction what I am getting here. Now similarly, if I take the another column, that is column CD, and if I take summation of moments about joint C in that column and equate it to 0, okay, what I'll get, I've drawn the free body diagram for CD and I am applying the condition of equilibrium, one of the condition of equilibrium for that member CD here. Summation of moments about joint C should be equal to 0. So what we have is HD into 2, okay, so this HD into 2 meter, so it will be in clockwise direction, plus MDC plus MCD is equal to 0. That should be my equation of equilibrium for member CD. When I consider summation of all moments about joint C equal to 0, this is what I will be able to write. HD into 2 clockwise moment plus MCD is the moment at joint C plus MDC is the moment at joint D. When I add up all these moments, that should come out to 0. Or I'll be able to write what is HD equal to. Again, what I'll do is except HD, all other terms have been taken towards right. So I'll get this HD equation for HD. So minus 1 by 2 into this is MCD 3ei theta C minus 9 by 4 ei delta. Okay, plus MDC 3ei by 2 theta C minus 9 ei by 4 delta. Okay, and that will give me what is HD. Again, it is in terms of theta C and delta here, HD. Okay, now what I have to do, I have to add up this HA plus HD and equate it to the applied force. Okay, in our case, applied force is 80 kilonewton. Okay, and the resulting equation, what you find here, after you take this summation fx and simplify the equation, that will be another equation which will be in terms of 3 unknowns. Now what we are left with here, 3 equations with 3 unknowns. 2 equations which you find in condition of this equilibrium. Okay, here 7 and 8 were the 2 equations in terms of 3 unknowns from condition of equilibrium. So, and also the shear condition is giving us one more equation in terms of 3 unknowns. So what we have is 3 equations and 3 unknowns. Now if I consider these 3 equations, 2 from the condition of equilibrium and 1 from the shear condition, I'll be able to solve for the 3 unknowns, okay, theta B, theta C and delta. And from that, we'll be able to calculate the moments in the frame, okay. So that is how the sway analysis procedure is, okay. Let me do those small corrections. I'll provide you with those small corrections, and also in the next this one, we'll check that, okay. Just try calculating this. Any doubt in the part of this procedure, that is in taking the sway sign, assigning the sign for delta, that is one part, and writing the slope deflection equation for the 2 vertical members, for the columns. That is the difference what you come across in when you solve these sway and sway frames compared to the non-sway frames. you can ask any doubts. I'll just stop it for now. And before I proceed further, what you have to do is in your chat box, you have to type your USN and your division. Okay. That will be your attendance. Your attendance will be monitored. So you have to type in the chat box the USN and what is your division. Okay. Everybody just post your USN and division. What we have come across now till now. In that, if you have any doubt, you can clear those doubts. Don't worry about the values. Values can be corrected. I'll check it. One is that fixed time moment MFAB and another HA plus HD. Okay, that should be 80. Only thing is at the end we'll come across this moment values being changed. Okay. Other than that, delta sign and what is the shear condition, how you come across that shear condition. Equilibrium condition you have been using in a non-sway analysis as well as in the beam part also. Okay, but here what is the difference is additional condition has to be taken into consideration, which will help us to solve the problem. Okay, that additional condition is this shear condition. Any doubts, you can just tell me. In tomorrow's class, I'll come up with the same problem with those corrected values. Only difference is these values will change. The procedure will not change due to that 120 kilonewton and this HA plus HD is equal to 80. These values of theta and moment values will change. Other than that, the procedure will remain entirely the same. Please go through the procedure, understand the procedure, what has been told. Okay. Okay, thank you. We'll meet tomorrow.